Okay, well, thank you everyone for being here. Congratulations to the candidates that made it here. This is huge for you. All the work is great. So this is a hard well, thank you everyone for being here. Congratulations to the candidates that made it here. This is huge for you. All the work is great. So this is a hard well, thank you everyone for being here.
I don't know what's happening. I'm hearing myself.
That made it
This is
here.
amazing.
This is huge for you. All the work is great. So this is
Gabrielle, are you there? I'm hearing myself over and over.
Are you with the YouTube tab open?
No, I don't. I don't have it open. Okay.
No, we should ask everyone to mute them. Yeah, now it's done.
Okay, cool. Thank you. No worries. All right, so welcome everyone. Thank you all for being here. This will be fun. Looking forward to the session. We have 5 today. Oh, I'm muted. Okay. So we have 5 presentations today, 5 candidates that are here. We're going to start with augmented architecture by Garvin Gopel, and then biotechnic by Maria Kupstova, and then the work of Akbari Mostafa, followed by Saeed Moran work in documenting crack disorders using artificial intelligence. And last but not least, Thiago goes. Okay, so we are going to go in that order. First of all, I would like to introduce myself. My name is Paula Gomez. I'm a PhD in computational design. I work at Georgia Tech. I'm from Chile. I'm in Chile right now. So I'm moderating this session because I'm part of the SIGraDi board. So yeah, looking forward to the session. Please, I would like Dagmar, Kathy, Alani, and Rudi to please introduce yourselves as well.
Yeah, perfect. Thank you. Welcome and good morning and good night to everybody around the globe who's zooming in here. Thank you for having me at the World PhD Forum. Super proud and happy to be here. My name is Dr. Dagmar Reinhardt, and I'm an associate professor at the School of Architecture, Design and Planning at the University of Sydney. And as is custom here, I would like to pay my respect to the Gadigal people of the Eora Nation, who are the original custodians of this country here. Thank you for having me, and congratulations to the candidates, and I'm looking very forward to discuss the presentations.
Thank you. Kathy?
Sure. Glad to be here. Glad to be here at the second WorldCAD PhD workshop. We were really excited when we launched this last year. It was a great success, so congratulations to the candidates for being here. My name is Kathy Velikov. I am professor at the University of Michigan, Taubman College of Architecture and Urban Planning, where I'm also the Associate Dean for Research and Creative Practice, and I'm also the Vice President and former President of ACADIA. So looking forward to all the discussions.
Awesome. Alani? Oh, it's Mostafa Alani. Oh, sorry. I was just reading your email. I think you're muted.
All right. Okay, so.
Oh, it's Mostafa Alani. Oh, sorry. I was just reading your email.
Okay. Thank you very much for having me here today, and congratulations for the candidate. My name is Mostafa Alani. I hold a PhD in Planning, Design, and Built Environment from Clemson University, South Carolina.
Oh, it's Mostafa Alani.
My
Sorry.
main interests lie at the intersection of computational design and
Thank you very much
geometry.
for having me here today, and congratulations.
I apologize as I still hear the echo. So I'm
hold a
gonna
PhD in Planning, Design, and Built Environment from Clemson University, South Carolina.
Okay, well, thank you. We have someone with YouTube on, so we can hear that. Please just mute your YouTube in the meantime. Right, Rudi.
Sure. Thanks for having me. I unfortunately wasn't able to attend last year, but I watched yesterday's and it was really really wonderful. So I look forward to this evening. I'm Rudi Stouffs. I'm an associate professor in the Department of Architecture at the National University of Singapore, and I'm representing eCAADE. As the president of eCAADE, I'm here tonight.
Well, thank you, panelists. And we have with us Federico Braida. He was the chair of this year's conference together with me. Fred, you want to introduce yourself?
Hi, good morning. I'm Federico Braida. Nice to meet you. And it's a pleasure to be part of the organizer of this PhD workshop and enjoy it. Thank you, Paula.
Yeah, thank you, Fred. Fernando is also here. He is the main organizer.
Hi, everyone. Thank you, Paula. It's a pleasure to be part of this organizing team. We are glad to have you and excited to see the presentations and the knowledge sharing that this workshop is all about. So thank you for all of the panelists and the presenters, and enjoy. Thank you.
Thank you. So we will start with the presentation of Garvin Gopel, Augmented Architecture. So Garvin, if you want to introduce yourself, and then I'll play the video.
Yeah, hi, my name is Garvin Gopel. Thank you so much for the opportunity to present here. I'm really looking forward for your thoughts and feedback on my work. I'm a PhD researcher at the Chinese University in Hong Kong, and specialized in the implementation of augmented and mixed reality in fabrication and design processes.
All right, great. So we will start, and then I'll ask each of the other candidates to introduce themselves, okay? All right. I'm gonna just share my screen. I have this one screen with me. Can you all see that? Yes. Is that okay?
Sound isn't playing. I think you might have to turn on sound when you share it.
Yeah, sorry about that. Yeah.
May I interrupt? When you're sharing Zoom, there's a little box at the left low corner that enables audio when we...
Got it. Thank you. All right.
We are about to enter a new digital revolution with the real world. Hi, my name is Garvin Gopel. I am a PhD student in my second year at the Chinese University of Hong Kong. I am specialized in the implementation of augmented and mixed reality in fabrication and design processes. and today I will present you my PhD research on augmented architecture. We are about to enter a new digital revolution, where the real world is merging with the digital. This digital overlay is personalized and contextualized by referencing itself to its surrounding with a sensory awareness, augmenting your needs and tasks. Accelerating developments in wearable mixed reality hardware devices have the potential to extend our human abilities and enhance our reality digitally. Spatial computing has the potential to radically transform our workspaces and our perception of reality. We are entering a new phase of AR, where the focus is shifting from a representation tool that displays general content on markers to a phase where mixed reality will be personalized, adapting and interacting with our surroundings and ourselves to create experiences that enhance our reality. AR holographic instructions in architectural design and construction context have the potential to produce an alternative to conventional 2D drawing practices by implementing it as an aid for assembly and fabrication tasks. The on-site need for human labor skill is increasingly reduced to the basic assembly of advanced kits of parts, pre-manufactured by automated processes. AR enhances human on-site agency and increases labor forces' capacities to participate in complex building processes. The project's main ambition is to identify and expand on the spatial design opportunities and construction-related impacts from augmented and mixed reality technologies integration into the architectural design and design implementation. More specifically, the aim is to reflect and develop on practical challenges and the implementation of AR 3D holographic instructions on assembly and fabrication in an architectural context, to develop a best practice guidance for AR manuals. This PhD study hypothesizes that AR 3D holographic instructions for assembly and fabrication will become far more effective than, for example, robotics or other forms of CNC production. This is because AR enables augmentation of on-site skill through the direct visual overlay of specific holographic instructions onto manual actions. This can have a substantial impact on vernacular architecture in regions and projects that involve untrained community members in the construction phases, as augmented reality applications have the potential to increase limited affordances on-site for complex solution spaces by making computational design tools more accessible. The employed methodologies are reflective practice applied on a variety of case study prototypes that investigate the implementation of holographic overlays to augment assembly, fabrication, and design processes. The study will compare several approaches for holographic aided processes by looking at a variety of AR techniques for assembly, fabrication, and design tasks. It will examine emerging technologies in the field of extended reality technologies, hardware and software capabilities to fulfill the requirements for seamless integration into the field of architecture. In addition, it will advance studies in collaborative, holographic-driven construction, expand opportunities for technology-infused craftsmanship, and reflect on workflows that replace conventional paper drawing-based communication with holographic instructions. The hypothesis this research project postulates and aspires to prove through the work discussed is to expand the locally available design solution space for AR 3D holographic instructions for assembly and fabrication. I would like to say thanks to all the people involved in these projects, especially to my supervisor, Paula, with whom I collaborated on the majority of these. If you are interested in more details, please reach out on social media. Thank you all so much for your attention.
Right. Thank you. Dagmar, would you like to start with the first question?
Oh, absolutely. Thank you very much, Gavin. Beautiful project content that you are offering here. And I think it's right on the pulse of the time, because the introduction of the Microsoft HoloLens, I think we've been really looking at how can that be adapted towards architecture. And I think you said in the video, it has the potential also to replace robotic constructions. I think there's a real argument in there in terms of usability and also introducing unskilled participants into work processes and let them collaborate with each other. So I actually do have so I think that's all great. I actually do have a question, and that is basically, what have been your experiences with the collaboration between participants and larger groups in the construction of these beautiful structures that you've actually been in very complex structures that you have been showcasing? And is there, so that's the first question. And the second question is there like a pedagogical approach to it where you take a user feedback or you place them in a sort of training framework so that they can take over particular roles?
Thank you, Dagmar, for your question. So maybe with the experience on collaboration in general is maybe so far, since in the past we didn't have access to too many HoloLenses, which now luckily is changing due to the availability of these devices. But in the past we had the most collaboration between people actually wearing the HoloLens and actually people who didn't have access to the HoloLens. So this was a collaboration between people which we called holographic instructors, who would basically verbally transmit the information that they would visually see through the HoloLens to other participants. So for example, they would hold the stick in the correct position while others would, for example, fix the stick. And the user feedback, I think, is so far just the general experience from people working with holographic instructions. For most of the workshops, actually, I've been working also with students who did not study architecture. So we have a program here in Hong Kong, it's called Design Plus, which is not just architecturally related and it's quite open. So for some of them, it was actually the first experience ever to build and construct something. And they were quite surprised actually by the information that they would get holographically, because if I would have given them 2D drawings, which I might have actually done, I think it would be quite challenging for them to follow these drawings, since they do not have any training or experience in transferring these 2D drawings into some 3D sculptures.
Thank you.
Right. Kathy, would you like to go next?
Sure. Yeah, really exciting work. And I think the prospect of AR assisted construction is, I think, very exciting. As I think that you outline, and there's a kind of breadth of use and contextual cases. So I'm wondering if, and this is less a question, but maybe more a kind of point of discussion, is how you categorize the different contextual and user groups so that your case studies can be a lot more kind of specific, because I imagine that they have different contextual uses. So you talk about, on one hand, prefabricated, digitally produced kits of parts, which have a certain degree of precision. And on the other hand, you have like the structure behind your photo, where you're using, let's say, natural materials that are less predictable, with less precise methods of assembly. And then you have different types of users. You have, let's say, on one hand, it might be students who are learning. So there's a pedagogical context. There could be construction workers who have some training in understanding how to, in a kind of language of instructions. And then you also talk about untrained community members, which I think is a very different problem, especially in terms of visual graphic languages of communication, how you how they receive information and understand it. So I wonder how you're thinking about these different, cases and which, from all of these, are you going to prioritize some or work on all of them, or how are you trying to parse those out? Because I think they're very, having that specificity, I think, is very important to the research and being able to evaluate its outcomes.
Yes, thanks, Kathy, for your question. I think what I'm trying to work on mostly is to work on materials and projects which drive to actually go away from this hyper precision, which I think our industry is shifting towards. And I think if you look, for example, at some robotic projects for robotic fabrication, it's either 100% accurate or nothing, right? So there's nothing in between. There's no error that is accumulating through this, right? So I think what I'm trying to do is to have this in-between stage, to maybe not, if somebody doesn't have access maybe to this robotic arm, or sometimes it's also quite hard to bring these heavy machineries to specific sites. So what's the in-between? I think the in-between is to actually augment the human by giving the human the instructions a robot arm could have, and then perform maybe a curved brick wall such as a robot arm could do. But maybe there are like some inaccuracy and tolerances in comparison to a robotic arm. But I think still, if you can accumulate this slight error coming from the human, I think you're much more flexible and much more fast, and you can have much more flexibility and much more, you can go to sites which are much more remotely and activate community members who do not have access to these machinery to achieve something which is actually going in the same direction, for example. And for example, if I'm working with bamboo is like a material itself, it's like quite unpredictable. So we're working with bending bamboo, and it showcases that there's so many parameters that you have to respect if you want to deal with bamboo. It's like the age, the moisture content, the species, and so on. And all these parameters are so hard to simulate digitally. So actually there's like this learning by doing through these AR instructions, which need an immediate update in the drawing skills. So you can't just update a 2D drawing, but what you can actually do with holographic instructions, you can in situation see that the bamboo that you had in your parameters and that you use for your structural analysis is actually much more dry than you expected, and it cracks more much faster than you were expected. So by just changing this parameter, for example, in Grasshopper and through the live stream that you have on the HoloLens, you have like this immediate update on the HoloLens, and immediately you have like the updated drawing or the updated shape available. And I think it's also this feedback loop and the instructions that make it like quite successful to, in comparison maybe with other techniques that I'm working with. And I know for the moment I'm just working on pavilion scales mostly and on sculptures to shape, but of course the idea is to scale things up and to actually maybe have like a bigger small scale project, which is basically coming from this augmented feedback loop that I was slightly touching on, to maybe have in the beginning some design, but then over the course you change it and maybe you have plus minus 20% tolerance to actually see where the project takes you while building it. So yeah, I'm still at the beginning of my PhD. I'm now like starting my second year. So I think these are all aspects that I'm still working on.
Awesome, thank you. Mostafa, do you want to go next?
Yes, thank you. Well, I think my question a little bit aligned with Kathy's question. But first of all, Garvin, your research as a topic is very interesting, and I'm really looking forward to see what you're gonna find with your research. So it's very interesting kind of topic. But I think my question is, can you talk a little bit about the structure of your kind of research, what methods you're gonna use to, because in one point in the video, you mentioned that the hypothesis for researchers become more kind of the AR tools become more kind of effective than the CNC and robotics in the fabrication. So if that is the claim, I just wanted to kind of understand or wonder if you thought about it, is how you're going to validate that kind of claim. What kind of methods you're going to use to compare? Do you think that you're going to conduct some kind of experiments and compare the CNC versus the AR or so on? So I just want to hear your thought about that.
Yeah, thanks. I think the structure, how I'm going to do it, or maybe like the research gap, which I found is the biggest at the moment, is actually that there's not much research done about the actual AR manual. So if we talk about, okay, what is an AR manual? What are holographic instructions mean in comparison to 2D drawings? And are they more immersive? Are they more effective than actually the translation of 2D drawings? And I think then is the next step is basically what can holographic instructions do what 2D drawings can't? And I think then is when the step comes with the idea of the augmented human, because you enable a human to perform actually tasks not as a robot, but you have the ability and you have like a computer vision as a human, as an overlay. And the tools are compared like just much more accessible, much more cheaper. And with each update, I mean, now HoloLens is like a prototype, but soon maybe we are all like in the next whatever years, we have contact lenses that show digital content and the whole cityscape will change. And I'm just maybe more focused on what is basically what is an AR holographic manual and what are like the best practices for this. Because for the papers that I'm reading about many peers who are experimenting with holographic instructions, is they all have specific softwares and specific hardware devices they use, but they don't really explain the instructions per se, how they are coming to the shape. And I think if you can structure this and maybe make like this best practice guidance for, okay, if you want to build something with AR guidance, what hardware is suitable for you? How is the menu looking for? How do you stream it? What's the workflow? I think this is something where I'm like really looking into just the, yeah, as I said, difference to 2D drawings. And then, sorry, the research method is, I think, action research, which I'm trying to do by basically doing prototypes, by building stuff, by experimenting, but also looking at peers and talking to peers is how they've done, seeing where the research is going in many other directions. I think it's like a big part also to integrate it with BIM, for example, which is like the other end of the AR spectrum, whereas I'm more looking into these materials which you can accumulate error with, and yeah, sorry.
Thank you.
Right, Rudi?
Sure. Thanks, Gavin. Really nice, very interesting work. And I very much like the idea of kind of like upskilling people. I mean, making it easier basically for them to participate in these activities. And I'm sure you have plenty of experiences from the experiments that you did. My question is, now obviously, doing this requires some preliminary work, right? I mean, 2D drawing might be quite automatically generated from a 3D model, but I assume that the AR I would assume that part of the work is really looking at some kind of balance between, or at least working with that in the sense of how to simplify or maybe automate even these AR instructions. So what are your thoughts on that with respect to your research objectives?
Sorry, I'm not sure if I understand your question correctly. You mean how to find the balance between 2D drawings and AR instructions?
No, yeah, I mean, basically, the idea is that the AR instructions make it easier for the people to assemble it, etc. but the harder work is to actually generate or create these AR instructions. So there's you move a little bit the work to an earlier stage. And I'm assuming that that's something that you're looking at as well, as in, how can this be simplified?
Yeah, no, you're completely right. I think all that you see basically is the last part where you actually see the augmentation of the instructions. And I think this is just the last 10%, maybe the last 5% even of the whole workflow, right? Everything comes before it. It comes just in the beginning of the design, even when you think, how can you basically, just such as with other drawings, but like, how can you build this? And then maybe also, how can you build this with AR? So for example, for the sculpture, which is my background, which you've also seen in the presentation, the whole workflow was basically based on the thought of how we're going to do the workshop for building it. So for example, we sliced it in 4 parts because we thought, okay, we're going to have probably 4 groups based on the people we have. How many HoloLenses do we have here? We have 4 HoloLenses available, so we can collaboratively fabricate with 4 groups at the same time. So that's why I separated it in 4 parts, for example, and then 4 groups working together on assembling single pieces, and then they all came together, and then 4 HoloLenses at the same time were working together with the densification. But of course, the whole workflow before was actually, okay, how can you use AR for such as easy tasks as drilling holes? Like, for example, you don't need any more measuring tapes, so there are no need to augmentedly display meters or centimeters, right? Which you would find on a 2D drawing, for example. So just the spot in 3D space as a hologram is enough to know where you need to drill the hole. So this is, for example, something that becomes, or that you can illuminate in a AR instructions. And then for the next step is, how can you iteratively make the sequence so that you can fabricate one stick after the other to have like a solid frame, and what do you need to holographically display as an overlay onto the physical site in order to give enough instructions for the instructor and also for the AR assistant to actually connect the pieces. And I think the main difference also to 2D drawings is that you're working in a one-to-one immersive field rather than having the 2D abstractions in your hand, which you need to translate, because once you actually one-to-one inside your drawing or inside the instructions, how much information is actually necessary and how less information can you work with. And I think then there comes like technical challenges as well about like how much can you actually display, how's the performance, do you live stream, do you have an application that you basically download on your phone? When is the phone handy, when is like the goggles more handy? For example, we did like a workshop where like the phone doesn't give you the depth perception. So how can you deal with assembling something with the phone without this depth perception? So then you have to rather work with silhouettes and with frontal views rather than being immersed with your glasses, for example. And I think this is really where my research is also going, is to basically say, okay, what's available, what tools do you have, what do you need, who's your audience? I think like if you want to give, for example, to uninstructed community members access to fabricate something, I think the easiest way would basically be an app that you download on your phone, which gives you all the instructions. Whereas maybe for some other more complicated or more, maybe not more complicated, but maybe more challenging projects is where you would develop a live stream to the HoloLens, but which would require much more work on site actually, right? So I think this is really, I think, where I need to do much more research and where I want to spend the next years on.
Great, thank you. I look forward to it.
Thanks, Garvin. So I'm supposed to be a panelist as well. I do have a question very quickly. I would like to understand the aspects that you are considering in this process flow. So you mentioned importing some material sheets, and then you mentioned humidity and flexibility of some materials. On the other hand, the usability. Are you expecting this to be faster, more accurate, safer, more safe? So if you could just briefly mention what are the specific aspects that go through this process flow from the materials to the user, like an entire process? What are you planning to measure there?
Yeah, so I think what I haven't done, which I maybe should do, is to have one group fabricating with 2D drawings, one group fabricating with AR on the same sculpture, just to really prove this point. But all the structures that you've seen so far are really quickly built. I think like 2 to 3 days on most of them, and they don't require too much time. I think the sculpture that you saw on the street was basically, I think, 4 days to have like the base frame, then maybe a few more days for the cladding. So it's really, really quick. And I think it's so quick because it's also quite intuitive. Of course, this is completely dependent on the complexity of the projects itself as well. But I think another really early project was at the Rob Arc 2018, where I helped Team Hologram in a workshop there, that we bended steel pipes. And we were actually bending the steel pipes in 2 days, where we fabricated the ETH in Zurich, a small scale steel sculpture, whereas like robotic arms, who are then back in Australia in our MIT, where you need like 2 robot arms to bend like the steel pipes, right? And then you can just see the effort of like 2 high costly robot arms, the scripting and everything behind this for bending 1 pipe. And you still need the human labor to transmit these sticks and assemble them by hand, right? And then maybe it's an exaggerated example, but it was just really quick to even bend steel. And of course there were tolerances. It wasn't maybe as precise, but you can just accumulate these imprecisions by the system. So if the system can actually doesn't rely on this hyper precision, yeah, you're so much more flexible, and you can deal with so much more materials such as bamboo, where it's impossible to deal with hyper precision and have like millimeter accuracy, right? So I think these projects are all really handy to use for AR construction. I think it's maybe not really challenging to do a detail of maybe a window frame or something, but it's easy to have like more robust, more rural materials, maybe such as earth casting or sandbags or whatever, like many more ideas to come. But yeah, I think this is also where I want to look for the research more.
Right, great. Well, thank you so much, Garvin. Great work. We're going to move forward for the presentation. Maria, you ready, Maria? So we are doing about 27 minutes per person, and your video is a little bit longer. So please introduce yourself while I'll play your video.
Thank you very much. It's a great honor, first of all, to be here. Thank you very much to everybody for organizing this great event. And I'm Maria Kuptsova. I'm working in a great place in Alps in the University of Innsbruck, in an amazing team of Synthetic Landscape Lab. I'm supervised by Professor Claudia Pesquero. And I'm looking to an architecture, not as a maybe problem-solving discipline, but rather like a research field which aims to establish equal and horizontal relationships with the environment that we live in. And I consider that here the technology is becoming equal and very important actor in this relationship, which is enabling basically the relationship between the natural and artificial systems. So my research that you'll see now in the presentation is focused on the developing a design technique which aims to learn the intelligence, I call it the intelligence of the natural systems and its organizational principles, and aiming to translate into the design technique by the means of machine learning, 3D printing techniques, and as well as establishing new material life cycles. I won't say long because I think I'd have little time, and I will be very happy to answer all your questions after the video. Thank you very much.
Hi, I'm Maria Kuptsova. I'm a doctoral candidate and research associate at the Synthetic Landscape Lab, Institute of Urban Design at the University of Innsbruck. I work under the supervision of Professor Claudia Pesquero. I'm going to introduce you my research biotechnique, implementation of synthetic intelligence into design protocols. Today, the Earth and the cosmos have been transformed into a gigantic technological system. The concept of nature is changed evolving its meaning from a romantic garden of Eden to a cybergonic form of living, understood as a natural technical continuum. Non-human agencies as machining algorithms, transgenic plants, and planetary viruses are equal actors within the hybrid reality we live in. The technosphere is included in ecological thinking. Technology embedded in the multiple objects within the landscape allows new regimes and metabolism to evolve. Through sensors and intelligent technologies, we are decoding the complexity of flows, behaviors, and patterns embedded within the landscape. We see a strong potential for an explosion of new design methods, taking form through synthetic biology and artificial intelligence. However, contemporary design computation is still centered around human and structured by our prejudice. Can we develop a design technique that could shape a new form of communication between human and non-human, replacing the anthropocentric approach with the design of cybergonic living systems? Biological organisms are operating with its own biases and mode of reasoning. The behavioral model of fungus, bacteria, insects, and animals can be understood as a form of intelligence which acts within the alien for us realm. Stratum of the landscape encodes and stores knowledge about the microclimates, microchemical compositions, and multi-species interactions. Machinic intelligence has its capacities to search, generate, and process information with an efficiency non-comparable with human capacities. We could consider machine learning as an instrument of knowledge magnification that helps to perceive features, patterns, and correlations through vast spaces of data beyond human reach. What if the intelligence of an organic system could become an input to a technological system with its own evolutionary algorithm? In this case, biological models could frame new biases for the machinic operations. The conversation between biological and technological systems would frame a meta-language, which can be considered as a synthetic form of intelligence. In order to propose a biodigital design system, my research is focused on a timber structure. Traditionally, architectural material has been classified as either structural or functional. In a natural system, it is difficult to differ between structural and functional materials. Biological matter is heterogeneous and informed through the direct relationship with the environment. Wood is widely used in architectural construction because of its mechanical, environmental, acoustic, elastic, hydroscopic, thermal, and aesthetic properties. However, the heterogeneous properties possessed by wood in its living state are usually considered to be rather problematic. To study the material organization of wood, the project uses a large database on the botanical characteristics of different wood species developed by the ArchiWood project. Microimages of about 1,000 species were collected and analyzed with different contrasting techniques in 3 anatomical cuts and in 3 different magnifications. The distribution of vessels and fibers indicates varied degrees of densities and porosities, as well as reveals the heterogeneous anisotropic properties of wood. These qualities, which are usually considered as a negative side effect, can be rethought and reused in a design of artificially alive systems. The research proposes the use of generative adversarial networks as a method for extracting these material organizational principles from an existing database of timber structure. Railgun 2 variant of GAN was chosen as the most studied in architecture. During the training process, GAN architecture forms a latent space, which can be imagined as a space of networks knowledge. A series of points can be created on a linear path between 2 points in the latent space to set up a latent vector. To visualize the internal and external morphology, the latent vector interpolation was translated into z-axis of a volumetric structure. In this process, the basic geometrical data describing the anatomical properties of a timber structure were extracted. This network of curves and surfaces describes the distribution of material as a behavioral pattern. A volumetric model is formed based on a point cloud data generated from transverse timber structure cuts. Fabrication technologies, such as additive manufacturing, allows for the development of adaptive fabrication methods informed by research in material behavior. Wooden-based filament is used as a 3D printing material, suggesting a new regenerative life cycle of matter from the wood in its living state to recycled wooden material. Material studies provide a new insight on how additive manufacturing can be used to develop novel approaches for timber construction. The use of a large-scale industrial 3D printer, VASP, allows the material experimentation at a larger scale. However, in the next steps, multi-scalar robotic system will be implemented as a fabrication method. This would make digital fabrication techniques available at even larger scale, as well as would set up a direct relationship of the fabrication methods with environmental conditions. Additive manufacturing, regenerative life cycle of matter, as well as introduction of machine learning-based design technique, suggest the scenarios where cyberganic wooden structure could be artificially grown by the means of intelligent technologies. It challenges the process of growth, decay, and ontogenesis, introducing a form of cyberganic living object, which become a part of synthetic landscape choreography. This project aims at establishing a design strategy which places biological intelligence into its basis, as well as points to the ability of reshaping the human-centered approach in a design computation. Thank you.
Right. Thank you, Maria. Great presentation. So how about rotate and start with Kathy? You would like to start?
Sure, thanks. So Maria, really compelling topic. I think also kind of beautiful work, and I think that it's a, as you say, it's a topic that challenges a lot of assumptions, and I think that making those, what those assumptions are, and then how the challenge of these assumptions kind of creates a new paradigm for our, both processes, but also expectations, I think is something that hopefully you'll really fill out in the work. I have a lot of questions, but maybe I'll start with a couple, which is it. And I'd like to kind of structure the first question within that kind of framework of the made versus the grown, and where made and grown are, where that exchange, how that operates in a cyberganic structure, and it seems to me at the moment the moment of the growth really occurs through the computational process. It's grown computationally, or at least in the structure that you've shown as your first, I guess, experiment. It's grown computationally and then kind of made. And things that I'd love to know is what you learned from this first experiment, and how you think about now the role of, let's say, metabolism, in the structure. I don't want to call it a thing. It's like, what do you call this in the new structure?
An object or
an object. I don't know. An object seems so object-like. And so like metabolism is very interesting. Is it connected to other systems? Is it connected to inputs and outputs? Because right now it is a kind of an object, which I'm kind of, it's a beautiful object, but I also want it to start to be connected with the with other biological structures or systems once once you make it. So I think, is there what do you see as the kind of horizon of this in terms of its its lifespan after it is made, and how? And then a second question, and I know this is how does the anisotropy now benefit these new structures, and how do you start to think about that in the research? And so those are just two of a lot of questions that I'd love to talk more about.
Thank you so much, Kathy, for your comments and for the questions. They are targeting exactly on the key points of the research, and it's always fantastic to discuss it. So I think that, well, first of all, I need to say that maybe there's, beside the design work, there is also a philosophical question that I target through this design work. And of course, I question the idea of growth, the idea of neutrality in general, stating that basically we are living in the world where we are not that natural anymore, and that even our natural systems, I don't know, all the alpine region, which is surrounding myself now is basically fully humanized, and all the landscape is not natural anymore. It's fully disturbed by human, but at the same time, I'm not looking to this as a problem and trying to solve this, but I'm trying to learn from this system and trying to find new ways of communicating with that. So by communication, I mean, okay, how do we build, or do we find new ways of living this environment now, and maybe looking not only to the human as a center of this question, but also looking to the other systems which are present there. And of course, we can very long discuss who is the end kind of point in this discussion, human or not human. There's like a very long discussion, so I don't go there. But yeah, from here, maybe I kind of come to your first question about the kind of a note about the growth. So yes, this growth is purely artificial, and I'm not aiming to make the material which is growing itself, or the structure which is self-grown, which is fantastic, but I just maybe don't target there, but more philosophically discussing the idea that the growth, even in our, I don't know, human body, now is affected by the programmed DNA, etc. So basically the technology and biology is becoming the same. And from here, we're also coming to the idea of the kind of a change of the relationship to a technology, which is kind of, I'm not trying to be a technocratic, rather than to say that, look, like biology and us in technology, we are fully integrated, and the technology is basically the natural system which is surrounding us. So, and I'm maybe saying too much and forgetting some of the list of the order of your questions, but basically, how do I, what did I learn from the first? So my first experiment was more thinking about the material system. So first of all, I'm trying to learn from this idea of the heterogeneous property of wood. And it's really fascinating that wood, while it's living, it's capable to keep the structural capability, provide the food, provide the nutrients, communicate with the networks of mycelium under the ground, and create all this very complex living system. So basically, I question, can we try to plug into the system? Can we learn from it? But of course, we will create absolutely purely artificial growth. I use this word cyborganic, which is cyborgian and organic in the same time, right? But it's purely synthetic, of course. So the idea was to experiment in this scale of the material and create, maybe I call it an object, but maybe this is like a pillow of material, basically the structure that I was showing. Here what I learned is, first of all, the work working with a scale, because here the scale, the resolution, and all these processes and the transition between the digital model and materiality has been very important. as well as I came to the idea of also working with beside the computational methods and the logic of the biological model, I came to the idea of also working with the material itself, and how can we, for example, recycle the wooden powder and implement it into the construction in a new process of 3D printing. So basically 3D printing also becoming this kind of system of growth. So that has been a first step that I've done now. And actually, if you're passing by Innsbruck, it's exhibited in the exhibition just next to the railway station. We have a beautiful building, Exhibition Potenziale 3. So please pass by and to see it. And right now, I'm doing the next steps of the experiment and thinking how I grow this system. And what is very important for me is to establish this direct relationship with the environment. And that's why I'm also showing some work on the landscape scale in my presentation, when I'm trying to learn the same organizational principles of the landscape and see how this might affect the design of an object, which will be keeping this idea of the biological structure or like biological behavior within its stratum, within its pattern. So, and I don't aim to create necessarily, for example, a system for cultivation of I don't know, of any plants, or a structure for housing, for sheltering something. So rather than maybe I'm looking at this moment yet more widely, how can we establish a design technique which would allow us to think differently about architecture and to think differently about the architectural process? Because I think the answer is not about the result, but the answer is exactly about this process. So, and I'm kind of imagining, like, what if we are basically placing at the very base of our design question the idea of communication with biological system? Will it affect our designing? Like, will it affect the processes that we are establishing? So that's maybe like a next step also, which is coming right now.
Right, thank you, Maria. We have about 15 minutes. So Mostafa, do you want to go next with the next question?
Yeah. Well, thank you, Maria. Again, very, very interesting kind of topic that you're working with, and very interesting exploration that you're doing in your research. So my questions, maybe I have two questions. One maybe a little bit more technical, and the other one maybe about your research itself, structure of it. So the technical question is about your data collection process. And if the data you kind of fed to your GAN algorithm was kind of a series of growth of the a single kind of tree, or is it like different kind of pictures of different trees? Is it governed by any kind of type for the tree or something? So if you can talk a little bit generally about the data that you employed in your research, that will be very great. And the other question is, to keep it short, what is your expected findings and how you kind of plan to validate them? So these are my two questions.
Yeah, second is more difficult. Thank you very much, Mostafa, for your questions. So yeah, I think the database is like the data set is absolutely important, of course, when we are working with the image-based machine learning techniques. And that's, I think, a fundament for the research. And I'm basing my research on the large data set of the ArchiWood project. So it's the scientists who are developing this data set, and they're collecting the section cuts of the different wooden species in a different environmental conditions. And I know that could be like criticized and also evolved this research part as a kind of collection of the data set. But yes, this is very wide data set of different species which are grown in the different environmental also condition. And I'm this data set is prepared in a different magnification scale and different contrasting techniques. So, and also different section cuts. Why I'm basing exactly on this one, because basically in order to have precise results in the training process, I needed very precise the data set and very large. This allows actually this kind of quite a high-res outcome. Now, and the fact that I have a different scales and different techniques for documenting this wooden structure allows me to compare the different section cuts and allows me to basically build up more precise model. So that's why this data set is open source and not collected actually by me. But I do know that there could be a huge step in evolution of this research by really tracking the idea how the specific type of the plant grows, how the different environmental conditions are affecting on the structure of the plant. And of course, there could be a lot of precision in that. And I'm actually very happy to see that now I recently found some scientists, I don't remember the names, unfortunately, and they just published a paper a month ago on the very similar research on the implementation of the style gun in the research of the wooden structure, but they are looking at it from the botanical point of view, not from the design point of view. So basically, I think this field is getting developed also in the scientific field, and they're very happy also maybe to get in contact with the scientists in the future. So that's the first question. How do I evaluate the work? That's a challenging question maybe for me to answer straight away right now. I need to say that maybe now, yeah, I'm in the process, and yeah, there should be a system and the protocol of evaluation of the result. But I honestly don't know how to answer you straight away to this question.
I think if I may say, that's totally fine, but this is something maybe you kind of need to think about it in your next steps. And also categorizing your data, I think it's something that you need to, to work a little bit on. And I know it's maybe very challenging, very difficult to collect the data yourself. It's going to be very time consuming, very expensive. So that's something I don't think you need to do, but maybe categorizing or find a way to categorize the data before have them in your GAN kind of is something you need to also consider. But fantastic research, very interesting topic. Thank you very much.
Thank you so much for your question and suggestion. You're absolutely on the point as well. Thank you.
Thanks, Maria. I really, I mean, it's very impressive, all this, it's such a variety of what you, are able to produce and come up with. So my question really is about, how do you find a focus, let's say, and how, how can you make this available, or, like share this with others? How would other people be able to approach this, given that, it's so broad and there's so many possibilities. You don't know where to start.
Yeah, well, of course we do share everything, and we do teach. I'm trying to establish also this methods together with my students, and very often with the students when we teach also together with my supervisor Claudia Pesquero, we also kind of brainstorm and bring a new research there. But I think that well, here some techniques are widely available now for everybody. Well, there is of course some limits, and the technology is available for everybody, but quite kind of open in terms of knowledge. And of course, we are preparing a set of digital techniques, which are also immediately becoming available online. And we are actually not writing them from the scratch. And there is a huge community of people who are working on that. And we are every time, based on the open source, contacting the people who are developing this, some kind of a base of the techniques. But I think that here has been a very interesting investigation for myself, how we could move from, because there's definitely one of the topics that I'm targeting is how we kind of approach the machine learning and the architecture, which is now a very popular field, and there is a great professionals are working on this now. And for me, it was a challenge how we transition from the image-based machine learning techniques to the three-dimensional. So, and that was for me a very great step, that we actually achieved some good steps in this, and thanks to this large database available nowadays online, we are actually capable to create a very high-res structure out of that. So, and that's definitely everything available online, and just I'm very happy to share and to discover all these techniques together, because that's not the only unique implementation. I hope that could be possible to discover it further on, not only in the architectural field, of course, in the scientific field, as I was mentioning as well. This is very exciting.
Great, thank you.
Thank you so much.
Thanks, Maria. Dagmar?
Yeah, absolutely. Thank you so much, Maria. It's absolutely stimulating. I think you're getting a lot of compliments here, which is halfway because of your beautiful way of gathering natural phenomena, which I think that's an attribute. Finding these key images and being able to present them in this manner, that's an attribute itself. But also then the continued processes that you have taken through, which are not only computational, but which are also going towards fabrication. So to me, that's really the full loop. I'm sort of somewhere with Mostafa on the considerations that I have for a project like that. And so it's beautiful. And I'm a practicing architect as much as an academic and a researcher. And to me, the question is always, does it have to become architecture? Because architecture is a functional and programmatic framework. It's extremely limited, and it's not really allowing you a huge realm of intervention. So I think what you have set out to do, and I think there was a keyword in there, was sort of biological landscapes. And so I think steering away from this middle scale and moving across this, very detailed scale, almost on a cellular structure, and then to move straight onto 1 to 1,000 scales, like urban topographies or geographical strata that are being revised. I think that's an absolutely fascinating possibility that you would have in there. So to me, two comments. One key comment is what is the scale in which you're operating? So that would be my main driver, to just cut it a bit more. And I'm quite liking this dance between these sort of two very different scales, because I think that gives you a different property. And then if you just allow me to spin this thought a bit more, I was thinking about this as some sort of substrata in the way that you print it, because we all know that the problem is really in the printing process, right? Because you're always so limited to the printing bed, or then you take a robot, then you need to make the robot mobile, and then, that lots of different complications. We haven't yet printed with drones, which we actually should do, because there's a different distribution system altogether, which would be aerial, but that's a sort of different matter. But so the second consideration that I had was, if you're producing something that is inherently organic and that doesn't need to be architecture, then maybe what you're doing is another layer onto this earth, which is able to be colonized by different species. And in the same way as barnacles are colonizers or oysters are colonizers. So you would go in and basically produce a feeder system for other organic biological species to come in there. And so the system, because I'm always trying to consider what could you actually do with that? I think that's something that would be quite interesting as a sort of in the context of erosion or regrowth or soil upskilling or renaturation within sort of endangered sections of our urban environment, or on sort of on the boundaries towards the natural environments that could be quite valuable there. Because then, and this is where I'm going full circle, because that would give you some performance criteria, and that would help you to evaluate if your system's actually doing what you wanted to do.
Mm-hmm. It's a fantastic comment. I do absolutely agree with you, and we are experimenting, as I was showing, in to working with this technique in a different scales. And basically, I'm also very fascinated by this multi-scalar approach when we can find not the same but very similar forces within the micro and the macro scale, and then we could also translate and kind of relate this to scales. And that's basically how I try to speculate in between these different scales. So, but I do absolutely agree that maybe this is not exactly in architecture, and this comes a bit, yeah, into the different, that's what I was saying in the beginning before the presentation. So basically I look more into the establishing of the relationship rather than of problem solving approach, which aims to, for example, create a sheltering or do any, purpose for an architectural scale. So I think that what challenges me. And yeah, thank you so much. I will meditate on your comments long time now. And thank you so much for the suggestion.
Thank you.
Well, thank you, Maria. We do not have much time. My question was very in the same direction. I was thinking, where do you think your approach will thrive? In which environment, what applications? It's kind of in the same direction.
Yeah. So basically, I'm not looking for a direct architectural implementation which aims to provide any specific means of, for example, cultivation and I don't know, sheltering or creating a specific infrastructure in the urban environment, but rather looking to the I would say the noosphere of Vernadsky and seeing this kind of merging of the urban and natural landscape within this system and creating, as maybe Dagmar was mentioning just now, looking more to the new system of kind of a population or they're growing.
Yeah. Yeah, I was thinking in situ resource utilization. They do that for, Mars, but on Earth, we also need that in some, specific areas, especially, restoration, even, forest or like nature areas as well. So anyway, very, very interesting and inspiring presentation. Thank you.
Thank you so much, everybody, for the comments. That has been a great discussion.
Great. Mostafa, you're next.
Hello, everyone. I'm Mostafa Akbari. I'm a PhD student in architectural technology at the University of Pennsylvania. It's my honor to show my research here, and I'm looking forward for your suggestions and comments. I hope you enjoy the work. Thank you.
Thank you.
Hello, this is Mostafa Akbari. I'm a PhD student in architectural technology at Polyhedral Structural Lab at the University of Pennsylvania, Weizmann School of Design. My thesis is named Cellular Funicular Structures. This research actually is divided to 3 sections. First, I introduce a novel technique to design single-layer shell-based spatial structures using graphic aesthetics. Then I mentioned the application of this technique in different scales. And finally, I introduced a fabrication method that I'm currently exploring. Graphic aesthetics as a geometrical form finding method describes the equilibrium of a structure using visual geometric relations. With this technique, actually, we can design axially loaded structures in which no bending occurs. This technique is based on a clear relation between form and forces in the system. In this technique, actually, the equilibrium of a node in 2D, which is named form diagram, can be represented by a closed polygon named force diagram. In 3D, a closed polyhedron can represent the equilibrium of a 3-dimensional node as 3D reciprocal diagrams. 3D graphic aesthetics is an extension of 2D graphic aesthetics in which we can design a variety of cellular structures for defined boundary conditions. But structural performance of these structures relies heavily on the buckling performance of linear elements. Also, fabrication of these nodes, the nodes of these structures actually is quite challenging. The question here is whether it is possible to convert truss-like cellular structures designed in 3D graphic aesthetics to smooth surface-based structures. Triple periodic structures with the geometry of minimal surfaces called cellulars have exhibited a great structural performance due to their specific geometric properties, specifically compared to their stud-based counterparts. A typical example of the geometry of cellular structures are triple periodic minimal surfaces as two manifold single layer surfaces with zero mean curvature and negative Gaussian curvature. Cellular funicular structures can approximate the geometry of cellulars using a novel technique in 3D graphic statics. In this technique, after removing extra faces in the form diagram, we can result in a two manifold discrete surface. By removing these faces, the surface divides the space into two subspaces, each of which is connected with a labyrinth. Applying the anticlassic subdivision to each set of SQ labyrinths in these sets results in a smoother version of the form diagram. In this subdivision, a tetrahedron is produced between each set of SQ labyrinths as a first diagram corresponding to an anticlassic node as a form diagram. These labyrinths can be used as a subdivision axis to subdivide the main polyhedron to a group of tetrahedrons corresponding to a discrete anticlassic surface as a form diagram. But in more complex situations, finding the labyrinth network intuitively in the first diagram is not an easy task. That's why an algorithm was developed to automatically translate the truss-based cellular structure designed in the context of 3D graphic statics to a cellular funicular structure. The algorithm starts with tetrahedralizing the first diagram to make sure that the form diagram only consists of 4 valency nodes. Next, it finds the labyrinth graph in the first diagram, and then it removes the corresponding faces in the form diagram to result in a two manifold geometry. Finally, the algorithm generates a smooth curved surface from the discrete surface using a smoothing algorithm like Catmull-Clark or anticlassic subdivision in the context of graphic statics. Using this technique, one can design a cellular funicular structure for a defined boundary condition and translate it to its counterpart, a cellular funicular structure. This technique can have a variety of applications from microscale to macroscale. For example, the method has been used to design and analyze the mechanical performance of cellular materials designed in the context of graphic statics. Using this technique, a cellular material with Schwarz P surface as the geometry of its unit cells was designed. One of the advantages of using this technique to design cellular architecture is in controlling the resolution of the geometry. In fact, by applying different level of subdivision to the same set of labyrinths, we can control the resolution of the geometry and from truss cellular version to shell cellular or cellular version. Also, by deforming the geometry of the labyrinths, we result in a new architecture in equilibrium for a new boundary condition. And finally, by designing new sets of labyrinths, we can design unprecedented cellular funicular unit cells. And also control the resolution from transpaced cellular to cellular version. Comparing properties of p-cellular architectures created by this method and the ones based on the trigonometric level set equation, we observe that their mechanical properties actually match well, and increasing the level of subdivision will result in stiffer materials. In addition to microscale, this technique has application in mesoscale or macroscale. But the question here is how we can fabricate these kind of structures in large scales. Fortunately, these structures already comprise 5 faces resembling a polyhedral surface. Therefore, they are a genuine candidate to be fabricated using origami techniques by flat sheet of material. We inspired from a technique named tuck folding. With this technique, one can obtain the folding pattern of a polyhedral surface out of a flat sheet of material with hidden tucks. In this technique, after mapping the faces of the polyhedral surface, instead of each edge and vertex in the folded state of the geometry, a gap named tucking molecule is inserted, which is actually responsible for determining the geometry of the surface at that point. At the end, these talking molecules will be folded to be completely hidden behind the surface. We use this technique to fabricate the section of one of the design specimens. This geometry consists of saddle-shaped patches. After generating the folding pattern of these patches, each patch was folded manually and attached to the others to result in the final geometry. Although using this process, one can fabricate a discrete cellular structure out of a flat sheet of material, the folding process of the talks is labor-intensive and also time-consuming. That's why for materializing this process, we are investigating a self-folding origami technique. In this technique, we can use a physically based simulation to simulate the folding process of a basic bending element from an undeformed to deformed version by calculating the total forces in the system and computing acceleration velocities and new positions of the mesh's vertices in the deformed state. Here is the simulation of the basic bending element along with the visualization of elastic bending forces in each vertex, and the graph on the top actually shows the magnitude of the total forces in the system, showing the system is in equilibrium at the end. In this simulation, we can control the magnitude of the different properties such as stiffness, material thickness, and density. By knowing the magnitude of forces in the system and the material's properties, we are able to materialize the folding using an active material such as wood or any shaped memory alloys in real world to construct a discrete cellular funicular structure. This is still an ongoing research, and currently I'm working on the simulation and materialization of the folds. So still this is continuing. Thank you for your attention.
All right, thank you very much, Mostafa. We are going to rotate again. So Mostafa, Dr. Mostafa Alani.
All right, thank you. Thank you, Mostafa. Very, again, nice presentation. And so what I kind of get from your presentation, you're trying to present of a way or method to design, then you kind of apply this method in different scales, and then you develop kind of a way of fabrication for the geometries that you kind of develop. So I just want to hear from you kind of a little bit about the potential applications of the output or the findings of your research, and yeah, that's basically what I have for you.
Thank you, Mostafa, for your question. Actually, according to the geometrical and structural properties of the group of geometries that I've chosen, which approximate the geometry of minimal surfaces, which can be found like in nature. Actually, these kind of structures have great structural capabilities, and they can be applied to different scales, from micro scale to macro scale. For example, in one of our collaborations, we are using this kind of geometry to design cellular materials, which can be designed and constructed in micro scale. Or, for example, they can create a spatial quality to be used as a, for example, building, for example, like the Toyota's building. Also, I mean, because these structures are scale independent, structures that are designed in the graphic aesthetics, in the context of graphic aesthetics, they're scale independent, and that's why they can be applied to different scale by just scaling the geometry.
I was wondering if I may add, sorry, Paula, but if you kind of looked at the possibility of kind of using the fabrication method that you're developing into be used kind of on space, or used with shape-shifting materials that shape-shift in response to heat or whatever kind of if that's something you can take somewhere else and it will shapeshift and take a different kind of form to be used for something else.
Yeah, actually, that's the goal for the fabrication part. So what I'm doing now is I'm using the physically based simulation technique to simulate the folding performance of the material. And then after that, I can have access to the properties of the material that I can use in order to materialize that system. So when I have the enough information for in the simulation part, I can use any shape memory alloys, or for example, like wood, in order to use as an active material to bend the system. So that's the goal for now, yes.
Right.
Mostafa, thanks for the for this presentation. It seems that a lot of work has already gone into this. I don't know how far you are in your PhD, but definitely it looks like a huge amount of work. So I was really wondering, what's your goal really to achieve? I mean, when are you satisfied with your work, kind of?
Thank you so much, Rudi, for your comments and question, actually. My main goal when I started this research was actually working with complex morphology and designing geometry with complex morphology that actually had a structural capability. I remember I started like designing in design studios in my master degree, and I was wondering these complex forms that I'm designing, how they can be designed like structurally, and how the students in design schools from pedagogical aspects can know what they're designing and how their design are in equilibrium for a specific boundary conditions. I became familiar with the work of my advisor, Masoud Ekberzadeh, who was actually work on cellular structures, which are stress-based structures. And I was wondering how I can just convert these kind of structures to surface-based structures, to manifold surface-based structures, and if I can increase the structural capacity and also use that as kind of like a form finding language to design complex morphologies in different scales. That was the goal, and that's why actually I also divided my work to two parts. The first part was the design part, which actually I started from my thesis in my master degree, and then I'm now in the middle of my PhD. I was able to just make like kind of like an application for the Rhino software in order to design these kind of geometries. And now I'm working on the fabrication part, because these kind of geometry are designed based on flat faces. So I was using actually this property in order to fabricate these kind of geometry from flat sheet of material in order to have a whole like a design and fabrication technique.
Thank you.
All right, thank you. Dagmar, would you like to go next?
Absolutely. Oh, sorry, I just needed to unmute myself. Thank you, Mostafa. How shall I say that? Thanks for this beautiful showcase of structures that are both efficient, geometrically complex, and extremely variable, as you have been showing today. I was also extremely delighted to see the Musmeki bridge again being mentioned in your presentation. So I'm really wondering in which way you would see something about these structures which we don't allow ourselves anymore, because structures as we have come to know them now are quite formal, or they are quite functional. We all know that there are lots of stadia outside which which have taken really beautiful geometries at this point. But so how do you see your system being applied in a sort of real life environment? I know it's a bit unfair because we've been playing with biological systems before, and but I'd like to pose this question to you because you may have some interesting answers for it.
So if I understand correctly, sorry, you're asking that what are the applications of this technique in real world? Yeah.
Yes.
Actually, the application can be like from micro scale to macro scale. I mean, we can use these kind of structures to either design, like either use as a material in material of a component in a structure. Like, for example, a cellular bridge, or for example, the whole structure can be used as a whole component, like, for example, a component for a facade that you saw as the metal piece that is fabricated in the presentation, or the whole structure can be considered as a space. Because as I mentioned, this technique is scale independent, and we can scale up this technique and these geometries, these structures to larger scale in architectural scale in order to create a spatial quality. Using the degree of actually using the degree of freedom in these kind of geometries, we can, for example, scale up some links in the geometries in order to, for example, kind of have like capability to design like different spaces in architectural scale.
Yeah, no, I completely get the point. So, and I think there's benefits in introducing systems that have wide applicability also across different scales. I think the benefit of a PhD is that you have, if you get to cut the question or to package the question, that it's very tight. You are able to actually achieve amazing results in a relatively short amount of time, because as we know, the PhD is a short period, even though it feels long at the time when you start or when you're in the middle, but it's finite. And then there's always the life after PhD, right? Where beautiful ideas can be continued into practice. So I was just wondering, maybe this, because you are in the footsteps of, and again, I just love these structures, you know, these very expressive structures. So I have a hobby obsession with Gaudi and both Candela, and I think both of them, I mean, Gaudi just had time, right? And continued to work on this. And but Candela, I think Candela had the sites and developed the systems and just went out and did it. So in this case, you know, it's really, sometimes I'm thinking PhDs can be strategized also quite well by thinking through which are the industry partners or which are the councils that might give us opportunities to shape our ideas further. I just wanted to drop that maybe potentially into your question set and into your head for further fruition. I think it's beautiful, beautiful work.
Thank you so much. Thank you so much. Thank you for your comment.
My comments are probably kind of echoing a lot of the comments already made. I think the kind of design aspect of, you know, the design methodology of the work so far is super impressive and really exciting, the way that you have started to develop the methodology for deriving these cellular funicular structures. And I think now you're at a kind of second stage where you're trying to find material strategies. And I kind of want to go back to Mostafa's question, because I actually would argue that they are scale dependent. So for example, shape memory materials only operate at certain scales you know, once you get to a certain size, there's just not enough force in you know, like a shape memory polymer or a shape memory alloy to really lift its own self weight. So I think that there is a scalar, I think there is a scalar question. And I think then both the material and its topology in the topological method of assembly would actually vary by scale. And maybe that's a way to kind of ask yourself the kind of questions that you might want this phase of research to answer. And I think also, I guess some of the questions that have come up is how you see these operating, because I think as far as I can tell, the cellular funicular structures seem to operate, they'll operate differently, whether they're placed in tension or in compression. And it's also another question is, are they, do you see them operating as just the cellular structures working structurally, or are you thinking of this as being, let's say, formwork for other structural materials? So I think those would be some of my, kind of very small questions that might help you kind of partition very specific questions you might ask of this next phase of research, where you're starting to look into how you make these, and then how they could start to be used.
Thank you so much, Kathy. Thank you for your questions. These are actually great questions, and actually they are the great challenges that I'm facing now in my research. So the first one actually for the larger scale, like using a larger scale self-folding technique, which haven't been used before, because definitely it has some constraints. Usually in the self-folding simulations, they don't consider the gravity that much, but for example, in the larger scale, gravity play a great role. And that's actually one of my challenges now, that I'm considering to, for example, kind of try to come up with a technique to minimize these aspects in order to be able to fabricate these structures in a larger scale. Regarding, I just forgot your next question.
I think I was asking, are they operating in tension or in compression, and then are they being used structurally as shells, or are they being used, let's say, for formwork? I think they're kind of minor questions, but I think they can help structure your research.
Sure, yeah. So actually, these kind of structures can be kind of like the work that Gaudi did, or for example, before that, they can be used as, for example, either like only compression only or tension only structures for a defined boundary condition, which is actually one of the benefits of this technique, or either they can be used as a compression tension like a structure, which we have the ability to consider, for example, which part of the structure is worked in compression and which part is working in tension. Also, this structure, for example, can be either be used as a whole, like surface-based structure, whole shell structure, or for example, they can be combined with cellular structure, with strut-based structure, as a kind of like a hybrid structure between these two.
All right, great. So just again, like 2 minutes. Thank you for your work. It's really, really interesting. And my question is about validation. It's usually a forgotten stage of the research for a PhD. We do research question, hypothesis, method, and then, validation is basically how you prove what you are researching is, correct or validated. So what do you think about that? How do you plan to, even if you haven't done it, how do you plan to validate your research?
So by validating, thank you so much, Paula. For validating, I mean, for the structure aspect, we are using FE analysis, for example, to validate the structural capacity of the system, and also, for example, for my next paper, actually, I'm considering constructing one of my structures out of concrete and use and physically load test it in order to validate the structural capacity. And I think the materialization part of my research, in the materialization part, is another part that I'm trying to just use to show that, for example, these techniques can be used in the real world as a real material.
All right. Well, thank you very much, Mostafa. Great presentation. We'll continue with Said Maron, please.
Yes. Hello, everyone. My name is Said Maroon, and I'm an architect and historical monument restorer. I'm a PhD researcher at the Beirut Arab University of Lebanon, and I'm so honored to be part of this rich conference. Thank you. To present my research with the title of Hello, allow me at first to introduce myself. My name is Said Maroon, and I'm a PhD student at the Beirut Arab University of Tripoli, Lebanon. And I would like to present my research with the title of Documenting Crack Disorders Using Artificial Intelligence in Monuments Restoration Process. It is known that restoration of historical monuments is related to the preservation of the past to the future generation. The techniques used in the restoration and materials have evolved through time, leaving behind them the data collection and the generating of drawing. Artificial intelligence is the wild new computerized future. This research aimed to establish a connection between both, from a side the artificial intelligence and the restoration procedure to optimize the process of the crack detection in order to build a comprehensive model for consolidation technique. Nowadays, used methodologies in restoration are all related to human interference, knowledge, and manpower. The data collection, images, measurements, and sketches are all held on site. This process can take for months and even years, leading to generating drawing manually, as drawings, facade plans, and others, or even creating a non-precise 3D models. As said, if there is any missing information in the procedure, in the dimensions raised on site or anything, we should go back to the site again, then we should go through the process again, over again, until we reach the final and exact drawings. Same goes for identifying the cracks and the defects and pathologies. Then these are highlighted manually on the drawings, and then creating the specs of them in order to get the final output that could be missing of data or anything that human couldn't keep track of from the first beginning, and the results would be not satisfied and missing of data or missing of these images. Then we go back to the site and go back to the same process again and again until we get the results satisfied. For many times, we should go back again and again until we repeat it. Nowadays, methods for generating technical drawing from the existing of site, as we can see here, an elevation of the inner court of Mayfu Monastery. The output is generated manually and transferring these images to a drawing by hand or using the computer and using Autodesk as AutoCAD and Revit. As said, all of the work is done manually and visually or even by images, and the dimensions on site written on papers, and some of them are transplanted from images. And we can see here a process of transforming the drawing from images to drawing, and even with all of the precision and taking care, the drawings won't be exactly the same as they exist on site, and the specs is based on the knowledge of the architect restorer, and it's gonna be creating a problem of repeating all over again and again. The documentation problem and generating drawing of nowadays techniques are all related to human fallibility, time consuming, to the limitation of tools, and to the manpower, where, as said before, in many critical places, there is no time Toulouse, as an example, the explosion of Beirut, where until now, many team of architects and restorers are still working today to generate and assess the damages. And that cost us losing materials because of the environmental issues as rain and sun and dust. Wouldn't be just perfect if the computer works together with the human knowledge to establish a precise and well-organized work within a short time of period. The research workflow is the whole process from the historical monument, photos and data collection, and to generate a model and recognition of the data with highlighting the defects, drawing with just from a single image, or as much as possible with the help of the machine learning into highlighting the dimension, and then to come up with the consolidation program, technique, material, and specs and BOQs in order to help the restoration and creating a good restoration technical file that could be used on site. The challenges and the know-how as self-challenges, being far from the domain, writing code was the first challenge that I think I will encounter, getting to know the proper coding platforms, collecting the data, approaching and being familiar with the programs, and an extensive knowledge in its usage. How to train the program and manipulating it to serve the designated research. The tools used to accomplish the work as Python, TensorFlow, Tinker, Jupyter, and OpenCV, and many others. The machine learning workflow is based on the setup of data, development of the model, recognition of the data, and then training the model and retrain the model and test it and retest it until getting the analysis in order to get the final output, which is the application that should be used later on in the research. The workflow of this project is going to cover 6 steps and parts. For the first one, from image to creating a display of images with the right scaling and stitching of these images. Classification of the images will be the second, and extraction of the drawings and GIF representation, extraction of the model and mesh generation, and even extraction drawing. As we can see here, in each stage there will be an extraction of drawing that could be used in later and in the restoration file. Image recognition, and then training and analyzing of the surfaces that leads to defect automated detection, and then highlighting the defects area, highlighting of the cracks, and dimensioning and coming up with the final results and final drawings with the specs and how these issues should be fixed and could be the help of the restorer. Development of the project. The project is going to be on basic work, large-scale work, and developed work. The basic work is creating the 3D mesh and crack detection and the image classification. The large-scale work is when we go to the large-scale image as facades and the whole building itself, detection of the pathologies on the whole building itself, and then generating specs for the overall, and then creating a full package product that can generate files and documents that could be used for later on. I would like to thank you very much and have a good day.
Yeah, thank you very much, Syed. So Rudi, I think we'll kick off with you.
Sure. Thanks, Syed. It was a very clear presentation, and undoubtedly very important work. To really, I mean, my assumption would be that it's not just a tool to assist, but it could also, the results could, in principle, be more accurate, even depending on what expertise people have, etc. My question really is, so you focused on things like data collection, etc. I'm wondering if the results that come out of this process, this, the machine, basically the automatic recognition, currently this work is presented in AutoCAD, in Revit, you said, but are there opportunities to do more with this information once you have all this, computationally available in these different ways?
Once you have all of the data, you can like from photos and other things, you can implement them in the computer, and then the computer will be testing them and retesting them and testing them using the labeling images that you already implemented as well, and then from them you can generate drawings that will detect all of the defects that they are in the image that itself. Is that what you mean?
Well, yeah. I'm thinking, is it possible to have a 3D model that fully accurately describes? A BIM model is great, but in the end, it's an abstraction really of reality, because everything is super smooth, and surely when the building is brand new, that could be quite accurate. But the buildings that you are talking about are incredibly complex, right? If you take into account all these cracks, etc. So yeah, that's where I'm what I'm thinking of.
Oh, yeah. Actually, I did a small application, and from a single image, or using 2 images or 3 images on a specific place, you can get the depth and you can get everything. It will create a mesh from triangles, and then in this mesh you can get all of these the dimensions of these cracks, and it's so specific and well done, actually, I think.
And then you could do simulations of the structural system in a way.
Yes, and I'm thinking of going more further, actually, in creating the specs how you can fix these cracks. Actually, I'm focusing on the cracks on the cracks right now. It could be general. It could be because we have lots of deficiencies and pathologies in the buildings. Example, the trees, and then rust, and many others. But in this research, and I'm gonna focus on the cracks, and then these the generated applications later on you can manipulate the coding of it, and then it can be used on many other things.
All right, great, thanks.
Thank you.
Well, thank you. Dagmar, you'd like to go next?
Absolutely. I love the work. I think it's and I was just going through again through the abstract, because so I think there's a couple of keywords which I'm extremely interested in. So, and that's really the idea of historical conservation. Sorry, my tongue. Coupled with computational design, computational data tracking, and then artificial intelligence. I think that's a really hot topic. Connection between history and restoration, and through what we actually have at our hands at the moment with these high data sets that we can generate and that we can bring back on the side. And so I think it's also really quite interesting to see what is the original data towards which what is now damaged can be compared, and are these data sets. So are you coming from a photograph by which you are then constructing the original surfaces, or are we also talking about full geometries of buildings that have been extremely damaged? So are we talking about sort of highly sophisticated 3D models of lost buildings, or partially damaged buildings that will be updated in the process?
At the beginning of the process, it's gonna start with photos, and then from these photographs, you can generate like drawings from it using the AI, and it's gonna be black and white drawings, and then these drawings you can use them in each stage of for the restoration documentation, and then from these drawings and the photos, the original photos, you can generate 3D mesh. And this 3D mesh, it can be transformed to like a 3D drawing that could be implemented, used in other programs and applications. And after this stage, we will get like the highlighting of the cracks. Let's say I'm talking about cracks now, highlighting of the cracks with red or different colors, and even giving the dimension of these cracks on the drawings themselves. And then as well, you can print them and use them. And then you can get, after that, after this stage, it will give you the specification of, you will get like a sheet, VOQ sheet and specification sheet of these cracks, their dimensions, their length, their size. I'm thinking about as well to create how to fix them and to in this application to create like windows that you can press on them and then choose the way that you want to fix these issues, and then you get at the final you get the BOQ, specific BOQ for this type of things.
Yeah. No, I completely get it. So I'm just sort of spinning off what is the larger context. So you have a real life problem, which is great, which you're trying to solve by the means that you have at hand, by using these photographs to identify the cracks and then to work on that sort of small scale resolution of that problem. I think what you have in your PhD is the kernel to like a much larger question. And that's basically how can we secure heritage information of buildings that are lost? It's a global problem. It's not just I mean, I appreciate that but that would have a superb impact if you can sort of contribute to that knowledge, how that can actually be done. What we're doing at the moment in the construction industries, again, we're working with these digital twins, right? So we're moving from the BIM model towards not only the design, but also the management and conservation and maintenance of these buildings. So I think in a way you can almost reverse engineer from existing buildings what actually needs to happen in order to secure them, to protect them, to maintain them. What the economic issues then would be with that, how many people would be available to undertake these tasks. So I think it's a fantastic setup. It's a great problem that you do have, which you can work with. And then the other thing that I just thought, we have heard about sort of AI construction and the HoloLens before. It's almost like, it just would be fantastic to take something like that and to use that in order to compare, sort of what has been lost towards what the conditions are now in order to accentuate and to use wider populations of skilled or non-skilled workers to reconstruct these damaged buildings. But I think it's a significant work. It has a great problem, and I would like to applaud you for finding something that is a contribution to society.
Thank you.
Likewise, I think this is a really interesting body of research, and I think has a really a lot of potential for impact. And I also was quite pleased to see this because I've spent quite a bit of time in a kind of parallel life with archaeologists on sites. So really interesting questions. I guess I have one kind of more specific technical question and then one kind of larger question. The more technical question is in the phase of your research where you're working with the AI software and the kind of detection, and I'm wondering if there is something to be learned from other fields that use AI for diagnostics, and particularly like the medical diagnostic imaging, and if you've looked at how they've how that field has started to use AI for diagnostics, where we have you have very different contexts. There's a high level of interpretation required, so it's not like defect detection for industrial designed objects. You're working with kind of almost like a living thing, and how artificial intelligence, where that field, which I expect is quite advanced, or maybe not in this area, if there's something to learn from that. That's my first question. And then the second question comes to the kind of latter end of your project, which is to start to develop a kind of method for kind of repair of the cracks themselves. And that's where I think you're going to run into limits to the image detection, because each building, each structure has a different kind of physics and chemistry of its makeup, and the it's not just the filling of the cracks or the restoration or repair is not just a physical process, but it's a chemical one as well. And I know when I've worked with restoration, on sites where there has been conservationists, they'll take chunks of each piece of rock and send them back to a lab for analysis to understand even what chemicals can be used and what methods are most most effective. So I wonder if but that's a kind of amazing amount of domain knowledge from another discipline that I think would be incredible if you can start to include into this. How do you bring in not just the kind of visual analysis and diagnostics, but how do you bring in domain knowledge from other expertise into the database, into the intelligence of this I guess it's a kind of software, or these different software bundles that you'll probably have to use for the different stages. And because I think that would be kind of incredibly valuable for retaining that and transmitting that kind of knowledge, if it can be embedded in the intelligence of the system.
Okay, for the first question, you were asking if they used artificial intelligence like in hospitals or something, right? I was checking actually the usage of the artificial intelligence in security system, and then detecting the face of human beings or in animals, and and I was like literally reading the coding of these systems, and from them you can manipulate the coding and change them. So the application, the program that I'm gonna create, gonna read the defects like 99% exact, and they're gonna be accurate. And for the second question, it was about sorry, I lost track.
It was about the I would call it the non-visual and maybe kind of chemical domain knowledge required for repair of the and stabilization of structures.
Actually, I was thinking when I was thinking about the project and the research itself, I was thinking that even if it's AI, artificial intelligence, and it's gonna be totally computerized, human can manipulate this program that's gonna be created. In every step, you can do whatever you want, and you can change everything in the application itself, and you can change in the data that you wanna give to this application. So let's say there is a wall made of cement, and the to detect this wall and the material of this wall, I'm gonna add lots of data related to the cement walls and images, and I'm gonna tag them and label image them that this is cement wall, and then and other walls like stone walls, it's gonna be stone, and then if someone is using this application, I'm gonna use this application to detect this wall, and it's gonna say cement, and instead of saying stone, I can change it in any stage I want. I can fix it if the wall was stone. So in any stage of this program, they're gonna it's possible for a human manipulation for the program itself, and you can change everything in it, even how to fix it. As I was saying before, they are gonna create like a table of specs that this crack could be fixed in this way and that way, and even they're gonna be like opportunity if someone want to fix it in another way, you can edit, and it's going to be shown at the end of the project in the BOQ that you're going to have with the quantity that you used for this area. That's why. Is that the answer? Thank you.
I think just thinking about that whole methodology, I think, is really important.
Thank you.
Right. Thank you. Mustafa, yeah.
Hey, thank you. Saeed, thank you for your presentation. Very interesting research that you're doing, and I think it's also very relevant as well. So thank you. So I have two questions for you. The first one is a little bit more technical as well, and the second one is about your research itself. So the technical one is about the size of the data that you collected. So what kind of, how many drawings, buildings, or things that you looked at? And the second thing is about the findings or the expected findings of your research, and how kind of it's related to the literature and other studies that have been investigating the same issue, if that makes sense.
I was working on a crack, just a simple crack. And for this crack, I used like almost 40,000 images. And from these 40,000 images, actually, if you want like later on, after the program was trained, you don't need these images. You will never use them. But to train this program, I used like 40,000 images, and from these 40,000, I have to classify them between cracks and no cracks, and then at the end, I got the result. If there is if it's 0.05%, it's gonna be like perfect result. You cannot reach like 0% of mistake, and this is for a single crack. And then but from a single image, let's say I have one single image, and from that image there is a crack and splitting and hair crack and the medium crack and different sizes of crack. You can label on one single image these cracks, and even rotate this image like 4 times, and then from this 4 times you can label each time, and then the computer, the AI, will understand that this crack is 4 mm if they find a gap of 4 mm black on the like in the image that you input in this program. And for the second question, it was about the findings. Like, can you explain more what?
Yeah. So other researchers have kind of, I'm assuming, have also investigated the same issue that kind of relevant to that. So I wanted to hear from you actually, what other researchers have kind of investigated, and what are your findings, or how are your findings kind of compared to those researchers? Okay,
most of things that I found related to this as a literature review, if that's what you mean. Most of them they were related to the concrete slabs in tunnels, or concrete slab in a highway, or in like bridges. And these are related, they use like machine, like 3D scanning machines, or laser machine, and they are specific to small areas. Like let's say, sometimes it's the area, it's like 10 centimeters by 10 centimeters. And from these images, they use different typology of work, and it's related to the color changing of the radiation going inside the wall of the radar, the color changing between green, red, orange, yellow, and then they overlap these colors, and then they get the crack and the dimension of the cracks. Most of them they didn't use like coding and stuff like that, but for the meshes, for creating the mesh and generating the mesh in the project, I found there is like a bunch of applications that are using this type of course of artificial intelligence to generate from images their 3D mesh. That's not the purpose of this research. The purpose of this research is to end up with a final result of full documents for the restorer that can be used later on, that can be used to restore this building. Thank you.
Thanks.
Right. Thank you, Syed. So I have comments as well. I would suggest you look into the Brazil heritage colonial churches. Some of the work is published in CAADRIA. They have worked in similar issues of restoration and heritage, and there's plenty of work there that I think it would be useful for you. So that's my first recommendation. And then more technically, this is closer to my area of expertise. So I'm wondering about that, the classification you have for the cracks. I was thinking there might be different type of cracks, like cosmetics cracks or structural cracks. So I would suggest going, a little bit further to identify not only like cracks or not cracks, but also like what type of cracks. And then, how can you actually fix those? I think Katie's suggestion is very, very interesting. Beyond, the image, let's say the regular image, right? Like pictures. You have other type of images, like thermal images, other type of images you could also incorporate in the same process that might capture some of these like chemicals and, other like domain knowledge that she mentioned. So I think it's very, very interesting. And, my main question is if you thought about this like classification of cracks and the kind of sizes of those cracks. You mentioned at some point that you rotated the image, and I'm wondering if that makes sense because structurally, the cracks have some orientation, compared to gravity. So, diagonal cracks are structural cracks. So what are those aspects you could capture from the image process that can help you move forward a little bit more detailed definition of cracks?
When I was saying about rotating the image itself, it was about the data that you're gonna implement in the AI and the computerized system that can understand that this is crack. So let's say I have an image, and this image could be used in all directions just to make the machine learning. It's about only the machine learning. So if the computer, because the computer cannot see it as we see it, it can see it from all the directions with the different axes. So when I get an image, you can, I was saying that you can label it in all directions, so the computer will understand it. If he saw it from different angles, it will understand that this is a crack, and then it will label it and highlight it and understand that this is a crack and give it its dimensions. And yes, of course, about using the other techniques as other than images and stuff like that. Of course, I was thinking about it actually, about using if you want to implement like what do you call it? What do you call it? The heat, UV images and other images. You can as well implement them in this in this program. But if I'm gonna go to this far, it's gonna be very big for me now. It's gonna be like it's the coding of this this much is already a huge project. So I'm gonna work on it little by little, hopefully.
Yeah, well, thank you. I guess my point is, you know, if you focus where, you know, your findings are going, you can, you know, kind of like reduce your work and move like straight forward to that direction.
Thank you very much.
All right, thank you very much. So Tiago, I'm sorry we're a little bit late, so we'll probably run over about like 15 minutes. Please.
No problem. Thank you very much, Dr. Gomez. I'm honored to be here with such a qualified panelists and peers. My name is Thiago Montenegro Góes. I'm a PhD candidate at the University of Brasilia. My main field of research is sustainability and environmental performance simulation. So maybe my project is a little bit more pragmatic and it focuses on optimization of the environmental performance on the urban farm. I'm looking forward for your feedback. Thank you. Hello, everyone. My name is Thiago Montenegro Góes. I'm a PhD candidate at the University of Brasilia under the supervision of Dr. Caio Frederico Silva. I'll be presenting my dissertation project entitled Zero Energy Urban Design, a Typological Environmental Performance Optimization. First of all, it's important to notice the impact of the building sector on the environment. About 32% of all energy generated on the world ends up being used on the building sector. Furthermore, about half of all raw materials is also end up being used on the building sector. This represents broadly 20% of all CO2 emissions. So reducing the impact of the building sector on the environment is essential to address issues like climate change. And to do so, net zero energy target on buildings is essential. Roughly speaking, net zero energy means balancing the demand side with the supply side of energy, especially with the use of clean energy. But it's really important to realize that it's not only about that. It's about also of minimizing the demand, so it would minimize also the generation of energy. Many studies recently have shown that looking at a single building at a time won't be enough to address this issue. So we should be looking at the built park as a whole, so we could speed it up the process a little bit, let me say that. Institutions like the International Energy Agency or the New Urban Agenda from ONU all been concerned with that. And these issues are really aligned with many of the Sustainable Development Goals. Our recent literature review have shown that this field of research is really new and in expansion, but it's mostly focused on the global north with mild and temperate climates, really different from ours in Brazil, and also focused mostly in energy generation and distribution. But recently, we've been seeing a new trend concerning urban planning and urban design. Furthermore, especially with since the pandemic started, many issues concerning environmental performance as a whole also arose. So many have suggested that we should be looking beyond energy efficiency, but with issues like thermal comfort, daylight comfort, ventilation, and urban comfort, like more in a regenerative design approach. So not really looking at one objective to being maximized, but also many objects, especially the indoor performance and the outdoor performance, which are real world problems, not like a research isolated problem. So the research problem of my dissertation is how environmental performance aided parametric design can add urban design to improve this holistic environmental performance, this regenerative approach. The main objective is to develop a computational workflow of urban design, conciliating the indoor as well as the outdoor environmental performance. The method that we are trying to implement is on Grasshopper, using Ladybug and Honeybee mostly. So we could have like 3 different objectives. In fact, there are 4, but we can combine 2 of them in one. So we would have like the UTCA metric to evaluate the urban comfort, the load match index, which is the PV generation and the cooling load combined, and also the useful daylight illuminance as the 3 objectives that we'll be looking for. And that will be optimized with the Wallace X solver. The main aspects we'll be looking at are different typologies like Nathaniel and all have been working on for a couple of years. And we have like different parameters to be evaluated, not only the typology, but the floor area ratio, orientation, and street width. We've been doing this multi-object optimization on 3 different cities in Brazil. The 3 of the most populated cities in Brazil, São Paulo, Rio de Janeiro, and Brasilia, which by the way have different climates. And what we should be looking at the end, the expected results would be a workflow, a computational workflow as stated, but also trying to look at the trends that we'll be finding and set up guidelines so urban planners that don't use computational workflows could also profit from it. Currently, we've been working with some tests, pilots, I may say, and have been working with an undergrad student, and we've been doing some optimizations, and like you can see on the screen. And some trends are interesting to realize, especially the diversity of typology ends up having a better result in the overall performance. And that can end up leading to some interesting reflections. First of all, we'll be looking to think about design or urban design, not like form-based, but on perform-based design. And also trying to bridge the gap between urban design and architectural design. However, we've been facing some challenges as well. The urban form is not as simple to make it parametric sometimes. And the development of the UCTA, it's also been shown to be a little bit difficult because in Ladybug and Honeybee, they are stored in SQL, so it's not really easy to transform UCTI to UCTA. And with the results that we are having, like analyzing them is also an issue that we're trying to overcome. So which statistical metrics and analysis should be employed is also the stage we are working on. Here are some core references, and thank you very much.
Thank you very much, Tiago. I guess we'll go back to Dagmar. Wanna start, Dagmar?
Okay, thank you so much for that. That was Tiago. That was a great presentation, and again, it's a very, very large topic that you are presenting. And I think what will be really interesting is how these different softwares will be coupled into each other. What I personally also find quite interesting is when you talk about zero energy urban design, is there scope for looking at different cities and how they're operating? And would you consider, like, if you're looking at real life examples or some sort of structures, what is the outer framework? So is there like what scale are you operating in? Because I think that can also be quite lead to quite large data sets, which might be quite unmanageable. So I'd be interested to hear more about that.
Well, that's an issue that we have been facing. At the beginning, we thought more like a real urban setting, more complex and larger, and that end up having been a major issue to, let's say, make it the process really works, and also evaluate the results. So we end up like in using the typological approach. So looking at the urban block, so we have a smaller size, a smaller land size, and we could have also a more directive parameters to be analyzed. So we have a large urban settings, maybe one place you have a different configuration, but it's harder to analyze statistically. So we try to make it smaller, like we said, like it's approach similar to Nathaniel. And so we could like have a more controlled environment on the simulations. So, but we had this issue because we tried something bigger at first. So we're trying to make like to fit that in the smaller settings. And also we try to think about more like an real urban settings, but at the moment that we're trying to look more like typological, so it's more generic setting.
Okay, but you're talking about environmental data, so it's the built environment obviously is just one piece in the equation, and by no means exhaustive. So in your abstract, you're sort of stating Sao Paulo, Rio de Janeiro, and Brasilia. So in which way will, for example, vegetation play a role, or site and wind directions or other thermal influences that might arise through particular positioning on the topography?
Oh, well, the concerning about, let's see if I understood correctly, but we're using like the weather file of the city. So it's one, let's say the direct approach that we use when you do building performance simulation, for instance. The ventilation, it's an aspect that is, well, let's say, quite computational intensive, especially considering the urban form. So to maximize this early stage approach, we're using the data from the weather file. It's not, let's say, the best approach, but it's been used from other works we've been seeing. So we went this way because probably we wouldn't have the computational power to do so. Vegetation is also, let's say, a really complex environmental aspect of simulation, because vegetations transpire. So we have an issue with that. It's not like a simple task to do so. So we're not like evaluating that. However, we could apply something like the urban, let's say, the topography of it with a GIS file, and implement that like we did in that that example that we shown. It's a real setting from our city, and there is the topography as well implemented. But we're trying to figure out which way we could make this study to evaluate more like a typological approach. So we won't go as far as that, because that's been shown to us to be really computational, demanding, and quite not being manageable.
Okay, thank you.
Yeah, thanks for your presentation. I have a, I recognize a lot of your struggles right now, because I was recently involved in a project where we tried to build a from scratch a multi-optimization software with climate analysis. So I was, we were also using Grasshopper and Ladybug and Honeybee and Energy Plus, and trying to multi-optimize with Octopus, and then have a kind of output. So and I'm happy to talk to you after if you want to email me, because I think, yeah, this is a really super interesting question. I think the idea of being able to run multiple early stage design options and get feedback is going to be crucial for designers and teams. And usually this is done, and to have this kind of integrated with a kind of ideation, you know, a moment of ideation as opposed to an analysis in a late stage design, I think is, and making this user friendly, I think is great. I think you know, maybe a couple of specific questions and maybe more comments than questions. I think drawing the contours around the, you know, what you're able to optimize for, I think is really important, because things do get unmanageable very, very quickly, and there's so many different factors. And so I think that, yeah, the advice to kind of be quite specific about what questions you're going to ask this tool or this software to optimize for, and also recognizing that it can't optimize for everything. I wonder also, this is a fairly new software. I wonder if you've looked at Climate Studio from developed by Solemna, which kind of combines a lot of the questions you're asking for into a single I haven't used it yet in depth, but a couple of colleagues who have say it's amazing. And so you might look at that, because it will also give you, you know, data on things like carbon, which I think is increasingly important for early design decision making, and a lot of energy codes and kind of renewable energy and things like that you might want to incorporate in your tool. And so I guess, you know, maybe I don't have a real question, but it's maybe a question of how do you, yeah, start to tighten into the actual question you're going to ask, or how do you draw the parameter, you know, of your priorities, because you obviously realize that you can't optimize for everything, and yeah, and how you kind of focus this in terms of what data there is, and then obviously there's a lot of data that we don't have, so things like carbon calculator, there's still, the data is very incomplete in that. And so yeah, this is not really a question, just maybe bits of advice, and maybe other questions you could be asking yourself.
Thank you very much for the commentaries. I will look forward. I have seen something about Climate Studio, but I thought, I don't know if I understood correctly, I thought it's more oriented to the building aspect or a single building evaluation, but I will look further on it. And what we're trying to accomplish, and what we have like seen this far, is that we should be focusing more on the early stage development. So aspects like materials, which were like important in the first stages of research, we sort of took it off for a while, because that's add another layer of complexity. It's a new variable, and so it increases the universe of design really more. And furthermore, if we're trying to evaluate urban comfort, that's important, but that also makes the computational side of things really more intensive. So we're trying to balance that. But I think you touched on a really important point for us, is what we are trying to do and how we can manage the variables, the input variables or urban form So we are more focused right now on the urban farm, this articulation between the inside and the outside of the building. I think that's a really important stage right now, because up until recently, it was really computational intensive to do so. And now we can try to, people are starting to do that. So we're trying to manage that more on the urban farm. Materials, it's maybe in a later stage or in a further research. But I'll look further on your suggestions. Thank you.
Thank you. Mostafa?
All right. Thank you, Diego. Again, an interesting project. So maybe this is more like a comment, but it's about the validation of your the output of your optimization algorithm. I think it is, in your case, critically important to validate whatever you're gonna derive and to justify the generated solution. And the other thing you might need to look at is maybe a little bit about the theoretical framework that underlay your research. That is, I mean, if you look at the Radiant City by Le Corbusier and the way by which the city was kind of generated, and the criticism that it received as it's kind of deliver nothing but lies, I think because it was based, mostly based on the function, not on the social context within this city. I mean, these kind of questions, if you're going to have like an urban planner in your dissertation defense, I mean, you would definitely get some of these kind of questions. Is this a livable space that we can live in? A space that is basically optimized based on kind of energy consumption and so on. So what about the other factors that come into play? I wonder if you thought about that, and if you did, I would, maybe we can hear about this from you. The other thing I would like, which is, this is my question, what is kind of the importance of having these different cities that you mentioned, 3 cities? I do think definitely you need to narrow down and you look at maybe a neighborhood scale or something like that. But what kind of research questions that on investigating these 3 cities is you are trying to answer? So this is my question. Thanks.
Thank you, Professor Alani. First of all, about the validation, it's something that we look for, we look further. But it's really hard when you have many multiple configurations, so it's hard to go and measure that. What we are aiming mostly is to use like methodologies that are more broadly accepted in a way, and especially because it's also early stage evaluation. As I said, materials don't play such a role on that. So it's hard even to match a physical setting. The second question about the theoretical framework, I think we can look, we're trying to implement something that is more like integrated with urban planning. It's not really my specialty. I'm more like an environmental side of things. And we do think that's important, but as I said in the beginning, it's multi-objective optimization. We're trying to, because in many studies, we may use only one objective to evaluate, for instance, the energy efficiency of a building. And that's limiting, and we understand. And doing a multi-object optimization, we start to have more like real-world problems. However, as you said, world problems are really complex. We have so many variables, and of course, for an urban designer or an urban planner, aspects of sociability, walkability, that will also be a really important issue. We are not minimizing that in any way. but we understand that there's a limitation for our way of evaluation this. For that example that I shown, we use basically the inputs for our urban code. So it's what the urban code enables us to do. So it's within that framework. We might wonder if we could like stretch a little bit that the code so we could see if things work differently. Also, in a way, we could like help planners to evaluate other alternatives of thinking about urban code. But we understand that's really limited, but we think that we're making a step ahead, trying to conciliate at least 3 or 4 different goals in our evaluation. Our group of study mostly works with environmental performance. And for us, it's really important to at least notice the differences of climates that we have. Brazil, it's quite a big country. You have really, might seem that's mostly hot, tropical climate, but we have at least different climates in here. So it's important to realize the differences that we have. And so we're trying to evaluate these 3 cities because they're the 3 of the most populated. So we could like end up giving back to planners, let's see, at least some orientation, some guidelines. And also they are 3 different climates. Rio de Janeiro is, let's say, one of the warmest climates that we have. And São Paulo is towards the coldest climates that we have, even though they're, however, somehow close geographically. So we're trying to see how different climates end up having an impact in these variables and giving it back to the planners in a way that they can use this feedback. But it's more about that. And at first we would do just one city, Brasilia, that's where I'm at. But in my qualifying exam, Professor Fernando suggested that since you end up building this framework, this algorithm, that's the hardest part. Applying to other cities will be like way easier than actually doing another framework. So it would be interesting doing so. But we will be looking for, I think that's a really important issue that you touched, to make it clear the theoretical framework about these aspects, that the complexity of urban decisions, and make it clear that's really a limited and narrowed evaluation.
Thank you. Rudi?
Yes, thank you, Tiago. I think it's really, you know, a very challenging but very important thing that you're trying to do. And I think especially looking at the, you know, trying to inform urban planning with this is very important. I mean, in my own work, we're using city energy analyst to analyze, you know, energy use over the city. But you know, it's not to be embedded into the directly into the urban planning. So you know, you kind of have this immediate feedback that you're looking for, and I think that is very laudable. My concern is that even though you are, you know, I understand you're not able to, you have to draw the line somewhere, and doing you know, ventilation, indoor ventilation is just, you know, way too far. I still, you know, I'm concerned that relying just on weather files might be, you know, too abstract or too simplistic. I mean, from my own research, I know that, you know, usually these standard weather files, they're quite old already. You know, things have changed. I mean, weather is changing quite dramatically in the last few years. Also, weather files are commonly based on measurements done at the airport or so, which are not really relevant. It doesn't take into account urban heat island, any of these. And if you have data available, you might be looking into, if you haven't done so, looking into and developing your own weather file is something that we've done in the past. But going beyond that, even if you have a relatively accurate weather file, there is of course such a thing as microclimate, and the weather file doesn't really. I mean, the way you create the urban context, the massing basically is going to impact wind, humidity, and that all these different factors. And I know it's very complicated. I wouldn't suggest to do some kind of airflow simulation. You lose the whole immediate feedback. But there are ways to simulate or approximate microclimate. At least one of my colleagues, Dr. Yuan Chao, has done a lot of work on that. I assume other people might have done as well, trying to find easy models to translate global information about weather to the more local, until the building. I mean, the building level is a bit exaggerated, but the small level in between buildings. So I would suggest to take that into account. I don't know how much opportunity you might have to look into that, but keep in mind that assumptions that you make may have a huge impact on the results. And if it's just about comparing A to B, that might not be such a big problem. But if you really want to get a good idea about the actual impact of the design, keep in mind, what the assumptions are that you're working with.
Well, thank you very much, Professor Rudi. I understand your concern, and I share, let's say, its concern. We understand that a microclimate is really different from the weather file, especially today, but it's really challenging, let's say, to at least construct a weather file that's more reasonably adequate to the settings. We looked at some alternatives. There is the weather file generator from Reinhardt that tries to, broadly speaking, try to accommodate a little bit more the urban setting in a generic sense, but make this translation. There's also some services to try to approximate to the climate change that we'll be facing ahead. But at first we thought going this way, but it seems that the scope was getting bigger and bigger. What we're trying to do, maybe that won't be really enough, because to really accommodate all these questions about microclimate, because with optimization, we end up having many hours of airflow simulations that will making that hard to do. What we're thinking, I don't know if you're going in the right path. That's something maybe you can give me some feedback on. It's an early stage evaluation. We work with EnviMat here on our lab really much. My supervisor is his main specialist, his main activity. But EnviMat is really computational intensive. So what we're trying to do is think, if we're working with early assessments, we might lose a little bit the precision. But as far as we're working with the design and narrowing the design a bit, we can do more computational intensive and more intensive evaluations, more precise evaluations. But at this stage of the research, would be a lot to me to do all of these stages. So we're trying to focus more on the early stage. So we're using Ladybug to evaluate the urban climate. I understand that doing a wind analysis of the site would be improving a lot the evaluations, but we are working much more with the urban form with direct radiation and emissivity of the walls and windows of the environment right now, because it has shown to us that it would be really challenging to implement that. But I share your concern about that, and maybe in a further research we could accommodate further stages of design so that will also be better answered, I think. But it's really important to explain that really well. I think maybe that's something that I have to work on in the recent stages of my work. Thank you.
Thank you.
Right, thank you very much, Thiago. I don't have a question, just I want to share some references. I know at Georgia Tech is not my area of expertise, but I know there are several dissertations on, urban sustainability analysis, energy analysis, wind, all of it. So I recommend you look at it. Also, I know Perkins and Will is developing some like real-time decision-making tools for this. We had a workshop at SIGraDi last month, and it's recorded, so I could share that with you. That's it, and we are way out of our schedule, so I apologize for that. I know Dagmar had to go. It was 1:40 for her a.m. in Australia. I just want to thank everyone. This is a wonderful, really rich discussion, wonderful presentations. Congratulations to everyone that got to this stage. I think your work is amazing. You have, a lot of potential there. Just keep working on it. I look forward to see the results of your dissertations. I don't know if anyone wants to share a last comment.
Just really exciting to see the range of work. I wish we could, sometimes it seems so abrupt to end right now. I wish we could kind of talk casually and have also the students talk to each other. And maybe next year we'll try to make a moment for that as well. Because I think there's a lot of, really, really interesting questions being asked and also the I think the methodologies that you're starting to look into and work with are really really compelling. So I'm really looking forward to seeing how all of these dissertations evolve, and hopefully seeing you present some of the work at future conferences and learning more about it. So great to meet you all.
I want to say that I really enjoyed your presentations and discussing your kind of projects with you. It's very interesting kind of range of projects that we looked at here today. The only thing I would say, sometimes working on the technical side might kind of, distract you from the research structure and what kind of question that you're trying to answer and so on. So this, maybe you need between kind of some time to revisit that and look into this, what exactly you're trying to answer. And whatever comments that you received here today that you feel you're not interested in addressing, or that this is not your focus of your research, maybe consider having that in your limitation section of your research. So just acknowledge that thing, and maybe this is something that you didn't look at. But other than that, congratulations. And I would also look forward to read your work and maybe see you in future venues. Thank you.
Yeah, thank you, everybody. For the wonderful presentation. With a great, evening for me, but it doesn't really matter. But I would also like to thank the organization it really nicely. Thank you.
Well, thank you, everyone. Thank you, Garvin, Maria, Akbari, Said, Thiago, and maybe Fernando, are we meeting again tomorrow at some point, like a wrap-up session or something?
Hi everyone again. Yeah, we are supposed to have the last session tomorrow, and we are planning a closing session. So it would be a pleasure if you could join us at the final moments, or even at the whole session if you wish. So yeah, we are open and looking forward to seeing you all.
Okay, great. Well, thank you again, everyone. Please don't forget the forms for the committee. We need to fill out those forms. Okay. All right. Great seeing you, everyone. Thank you very much.
Thank you so much for an amazing day. Bye-bye.
Thank you. Thank you, everyone. Thank you so much. Bye.
Bye-bye. Thank you.
Thank you, everyone.